Welcome. Today we will discuss on the next part of octahedral, that is type 2. The previous class we have discussed on type 1, and in type 2 we call that is D2, D8, D3 and D7. So previous class what we have discussed? Previous class we have discussed type 1, that are D1, D9 and D4 and D6. This type of discuss, and for this that Orgel diagrams we have to do like this, and here that D4 and sorry D6 and D1 of octahedrals, and D4 and D9 for tetrahedrals. This is like we will look for three orbitals. They here that Tg is there, here T2 is there, so here we will do the T2g, here we will do the Tg. Okay, and that D1 and D6, sorry, D6 and D1. Okay, so these are the D6 and D1 and D4 and D9 of this. Is to follow this type of transitions we will see. Okay, similarly this is Eg and this is T2g. So for this case, here D6, then this is for octahedral. Now this will become tetrahedral. Tetrahedral D6 and D1, and octahedral that is D4 and D9. So this follow this type of transitions. Okay, that we have discussed in previous class. Also we have seen that is for that D1 and D9s, D2 and D8. So the adding 2 we will get 10. Okay, so D3 and D7s, D4 and D6 and D5. So this will follow. This will give that terms for this will be 1. So this will start with D, D2, and that is we have remember D, F, 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 D, S. So D, F, F, D, S. And this is 2. This will be 3. This will be 4. This is 5, and this is 6. Previous class we have discussed on D1 and D9, that will follow this spectroscopic terms. Another is this one, D4 and D6. This spectroscopic terms we have discussed in the previous class. This is all in type 1. And we have seen that this type of will keep no spectroscopic. This types will keeps no Orgel diagrams. This will give no Orgel diagrams. Okay, so this we have seen that D5 they will not give no Orgel diagrams. And for today class we will discuss on this. This will falls in type 2. Okay, so today we will discuss this type 2s, and also we have seen that this spectroscopy terms SPDF. So we have seen that this S, that molecular notations for octahedrals and tetrahedrals. We have seen that for S this is A1G and this is A1, and for T1 we see that is T1G plus T, sorry, that is only T1G, and this is T1. And for D we see that is T2G plus EG here, T2 plus E. And for F we see that T1G plus T2G plus A2G, and here T1 plus T2 plus A2, because here that no G or E will not come, because here that no COS is present. So these things we have discussed in the previous class. Okay, so today we mainly discuss this type 2, that is D2, D3, and this fall D8, D7, and this fall on FF. Okay, and this F molecule notations are these things. So whenever I am writing in D2, D8, that spectroscopy terms will be F3, and this F, then the molecule notations are this. Okay, T1G, T2G, A2G for octahedrals and tetrahedral, T1, T2 plus and plus A2. Okay, so let's start type 2. That are D2, D8, D3, D7. These are the type 2. Okay, and this D2, D8, D3, D7 only for F. Sorry, and F means the molecule notations are T2, T1G, T2G, and A2G, and for this T1, T2, and A2. Okay, so first we will discuss on D2. Let's say this is for octahedrals. If I now draw that from, then this will 1, 2, and what we have seen that this type 2s, but they have more than one hole or electron transitions. Okay, so it has unlike type 1, there is only one hole or one electron transitions was there, but here in this case it has more than one hole or one electron transitions is present. Okay, so now if I pull for D2 octahedrals, then let's say I will fill that 1 and 2. Okay, now you see here that how many electron transitions are possible. Then we see that 2 electrons are there, so 2 electron transitions can possible, because they will not change its spin, because this can also transition do, after that this also can do. Okay, so electron transitions is possible is 2, and for hole that possible is how many, that 1 and 2 holes are there. Okay, so hole also 2 is possible, so we can do either electron transitions or hole transitions. So we can do hole, because both the cases there will be no problems. Okay, so now we will do that hole transitions, and sorry, electron transitions, and 2 transitions are possible. Let's say this one, and okay, so one transitions I did. Okay, so this will get transitions. So now what will happen, that this is there, this I do the transitions. Again transitions is possible, so again I will do. So again this one I can do that, then this and this. Okay, so these are that 2 transitions are there, I did the 2 transitions. Now, so for case of type 1, only one transitions I used to do. For here I did the 2 transitions. This is the first transitions, and this is the second transition. Okay, so for this, now what I will do, that I will assign the value where non degenerate states are there. Okay, so let's the assign. So here degenerate states is there, here is also there, here is also there, here no degenerate states are there. Okay, so I will assign that where the degenerate state is there. So for this case I will write T2, so this D2 fall in, you see that D2 and D8 fall in that F3. Okay, this we have seen that D2 and D8, that spectroscopic term is F3, and this F gives that T2G, T1G, T2G, and A2G. Okay, so this D2 and D8 fall on that F3, and it has that spectroscopic terms of T2G, T1G and A2G. Okay, so if this is 3, then I will write 3, 3 and 3. So this falls in T2G, T1G and A2G, and this is 3, so I will write 3, 3 and 3. Okay, so now the question is that these 3 terms are there for this 3. Okay, so you know that E generate that triply degenerates, and A denote that non-degenerates, and if E is there, then that denote that doubly degenerates. But we have that no E is there. Okay, so we will not, E is not there, so we have to talk a T is there, A is there. This is, let's say, T1, another is T2 is there. This also triply degenerates. This we have, these 3 things you have in F3, and that is fall in D28. Okay, so if here the from within this we have to assign these values, because for this spectroscopic terms of F3 we have this Mulkey notations only, we have no E, so we have to assign anyone to these values. Okay, now what I mean that here that non-degenerate states are there. Okay, so for this A is given, so I will assign that A. This is A to G, since this is octahedral, so I will assign to A to G. Okay, now this and this has left, so here that one concept we will apply. That concept is, let's say we have that with d orbitals we have, if let's say this is the d orbitals, we have that dxy, dyz, dzx, dx square, y square minus y square, and dz square. Whenever it's split it off, let's say this is dxy, dyz and dzx, and this is dx square minus y square, and this is dz square. Okay, so now what we say that we know that in chemical bonding we studied that dx square and y square. So from here also we understand that the general concept here, how many x's are the x and y has used here, x and y is used. So if the electrons, let's say, or it's better to, okay, if it is that dx square minus y square, and this is dz square, and this is dxy, this is dyz, and this is dzx. This is the one case. Another case, let's say dx square minus y square, this is dz square, this is dxy, dyz, and dzx. Okay, another case, dx square minus y square, this is dz square, this is dxy, dyz, and this is dzx. Other case also possible. Let's if electrons is there here, 2 electrons are there, likewise let's see 2 transitions I am doing. For this case I am doing that. Okay, for this case, okay, because 2 electrons are there, one is at EG, double degenerate, and triple degenerates. Okay, these 2 cases are there. This one, these cases are possible. Electrons can be either here, sometime here, sometime here. So that I am talking about up here. Okay, so if electron is here and another electron is here, okay, and also possible that if electron is here, also possible that if electron is here and electron is there, okay, also possible that this is dx square minus y square, this is dz square, this is dxy, this is dyz, this is dzx. Okay, also possible that if electrons sometimes here and also here. Okay, so these all are the possibility case. Now we will see that how many axes have used. Okay, so here we see that here we see that dxy, so x y is used, and here also xy is used. So two axes are used, means that here we are that two axes if used, then it has and two electrons. So if two axes and two electrons it has used, it means it will be have more repulsions. I write two axes and two electrons, so it will have that more repulsions, then it will have that high energy. Okay, so if it is high energy, so it will have that high CPSC values, and if you had high CPSC value, means this is not stable. Okay, means this may be the excited states. If the electrons are here and here, on that case what you see here, that electrons are used, this is x is used, y has used, section by here z also used, means that three x's and how many electrons, two electrons, three x's and two electrons. It means that it will have the less repulsions compared to this, less repulsions. So if less repulsion, then this will be less energy, and more stable. Okay, for this case we see that negative CPSC value may be there. Okay, so this also possible. Okay, if two electrons are there, because we are talking about this type of this type. What are the possible cases it will have? Okay, also maybe it is like that. Here how many axes are there? X, Y. Here Z is there. Y, Z. So Y already used. So Z. Here again that three axes and two electrons. So this will have the less energy presence, less energy, so more stable. So negative CPS will be there. Okay. Similar case here. How many axes? X, Y has used, and also I used X and Z. Z axis. Okay. So here also that. Three axes, so two electrons, so less repulsions, and this have the more stable. Okay, so the negative CPS will be there. So whenever that this type of possibles where the two axes, two electrons, okay, here the two axes, or also this is possible that if let's say electrons is here, let's say if electrons is there 2xy, 2yz, 2xy, and let's say if electrons is here and here, then also you see that two axes and two electrons, like yz and z square. So this is also have that high repulsions, and this will be the less stables. Okay, this type of things are possible. So these are the possible cases where that electrons, what type of this states will be possible. Sometimes this will be that high CPSC, sometimes it will be the negative CPSC values. Okay, so these types I have shown like these cases. Okay, so now we will discussing about a D2 octahedral case. For D2 octahedral, so these are the types 1 2 3 1 and 2. Okay, I am doing that excited states here. So one is excited state. Okay, okay, so now I will assign that for D2, that is F3. So for this you see that T2G is there, T1G is there, and A2G is there. So I have to assign this three values, 3 3 3 3. Okay, so I have to assign these values. So from here I understand that since this value is non-degenerate, so I will assign this to this A2G. Okay, and now I will assign these things. So we see that for 3F3. Okay, so previous class we have seen that this one, this is for that ground states. Okay, this is the ground state, and excited state is there. For excited states, But you see that for this we have that 3p, and for this we have that 4p. Okay, this we have discussed in that when you are discussing on the past class. There also we seen that this d2 d8 have that excited state also present, 3p and 4p. Okay, ground state is this, and excited state 3p and 4p is also present. Okay, so this I assigned the T2G. Now here excited state is also present. Okay, so now I will have to assign this between these two. So here what you see that calculate the CPSC values, and you see that here one excited state is there and ground state is there. Okay, so first calculate the CFSC value. So CFSC values, if I calculate, then this you see that this is 0.6 octahedral, and this is minus 0.4. So this is going to be minus 0.8 delta T. Okay, here CFSC value is that is going to be minus 0.4 plus this is going to be 0.6, that is going to be 0.2 octahedral. Okay, here CFSC is going to be how much above is that, then that is 1.2 delta knots. Okay, so from this CFSC, so always you see that this value will be never be the ground state. Okay, because here the two degenerate states is there, here also degenerate state is there, here also degenerate states is there, so this never be the ground state. Okay, these states never be the ground state, never be the ground state. This can be the ground state or this can be the ground state. This can be the ground states and this can be the ground state. Okay, okay, so this can be the ground state and this can be the ground state. So now what we see here that these values never be the ground state means I will assign that excited state to this value, because if I assign this anyone, then this can be the ground state. So excited state value I can't assign here. So here what I will do, that I will assign one as the excited. So these two I will assign that here. This two, this one already I assigned, so this two has left, and the other two are degenerate state is there. So what I will do, that T2G plus T1G, here this is excited state. Always do the T1G as the excited state. Okay, so this I assign to this value. This may be here, this may be here. Okay, but I will say that T2G and T1G for this full terms. Okay, and then what has left, since I already used that A2G, so here I will use that T2G. Okay, so generally they use T2G, not T1G. So T2G here, that for these two, T2G and T1G, because this cannot be ground state, so I will assign that, because here excited is also present, so I will assign that this is the T1GT and T2G. Okay, because this can never be the ground state, because two are degenerate states are there and its CPS value is always high, and it cannot be a ground state. Okay, sometimes it can be a ground state, sometimes it can be a ground state. So here I can't assign that this excited state. Okay, I will assign this excited state. So here also two degenerate states is there, so I have to give the two values, one for this, another for this. That's why I give the two. Here only one is there, so I will assign the T2G. Here all are non-degenerate, so for non-degenerate A2 is assigned, so A2G. Okay, so now how to do that Orgel diagrams for this. Okay, so if I do that Orgel diagrams, uh, this is that energy, the ligand field strength. Okay, so which value is ground state here? In this case, from CPS you understand that which is the ground state. This is the ground state. Okay, ground state means that low CAPC. Okay, so what I do here, F3, so this has that molecule notations, one is here, another is here. Okay, so this is the 3 T2G and its CPC value is minus 0.8 delta naught. Okay, and another is this values. Okay, this may be the past excited, it may be the second excited, but it never be the ground state. So this is 0.2 delta naught, past it will come, after that it will come. Okay, so this is or this is the ligand field strength, this is energy. Now what I do, okay, this is that F3. Okay, here it is T2G and this value is minus 0.8 delta naught and it got the values 0.2, that is for T2G and T1G, and this is T2G plus T1G 3 3 and 3, its value is 0.2 delta naught. Okay, and another is A2G, that's value is 1.2 delta naught. That is A2G 3, that is 1.2 delta naught. Okay, now what you see that excited states I will draw here. Okay, so that excited states will be that it will comes like this, that is 3p, and this value will be somehow like this. And since this is that this excited state is what, this is that 3T1GP and this is A2G. So we see that whenever the lines of different symmetric, when the lines of different symmetries approach each other, they may cross each other. So this is T1G, this is A2G. Okay, T1G and A2G, these are the different symmetries. So when the lines of different symmetries approach each other, they can cross. They can cross. So that will be they will cross it up. Okay. If the same symmetries they will come, they always repulse. They never cross. Okay. This is the crossing point. Crossing point. Okay. So this is that Orgel diagrams. This is the Orgel diagrams for D2 octaedral. Okay. So now what we see that here, now we have to understand that where is that delta nodes. So in this class we are discussing that where that delta node is, where, so where the transition is happening, that we used to show in type 1. So here also we will calculate that delta node. Okay, where the delta node will come. So one more thing you have to note is that in this diagrams, okay, before crossover of points, this is the cross points. So before cross points, here that here we will calculate that this delta nodes is calculated, delta node calculated before crossover points, before crossover points for weak field ligands. Okay, so this delta nodes here we will calculate if that ligand is weak field ligands. And here after that crossover points, after crossover of points delta naught calculated for strong field ligands. So you have to look that whether this is weak field ligand or strong field ligands. If weak field ligands is given, then we will calculate that before crossover points. Okay, if that weak field ligand is given, then we will calculate that delta naught somewhere from this. And if the ligand is strong field ligands, then we will calculate the delta naughts after this. Okay, after this means that it will go extended like this. So here see that this is that these accepted states each here, and here we see that this is that p t1g is here, and this is that sorry, a to g, this is for a to g, and we see that here this is the t1g. Okay, this is that for t1g, this is p, so this is t1g, and this is t2g and t1g. So there will be the start repulsions because this and this are coming this and this, they are coming closer. So if whenever that same symmetries, if they approach each other, they always repulsions, they will go away. Okay, so this what and that after repulsions, here after crossover point, this will since this is t1 is there, this is also t1, so this will start to repulse like this. Okay, and it will go like this. Okay, they will repulse, and this will be coming like this. Okay, so that I noted in the past class when lines of different symmetries, sorry, same symmetries approach each other, they always repulse. So this since they are coming to each other, so they will repulse. Okay, so this repulsions will happen. So after crossover points, how you calculate the delta nodes? So whenever that line is bent, so it is not sure that where it is, so we can't calculate the delta node if and that is line is bent. So we will look that which line is not bent. Okay, that there only we will calculate the delta nodes. Okay, so this delta node, it is calculated where the lines are not bent. Okay, if lines are bent, then we can't calculate the delta node because that will not give that exact what it is. Okay, because they are the bent, they are bending. So which are the state delta node? It is calculated where the lines are straight, and after adding we should get adding should be 1. Okay, after adding should be 1 values we should get. Okay, so here that before crossover points we can easily calculate the delta nodes because here that lines are not bent. Okay, so this is 0.8, this is 0.2, this also we can get the delta nodes. That is delta node is this minus this, that is 0.2 minus 0.8, that is going to give 1 delta nodes. Okay, so that should be 1, and this is the node should that should not be bent. Okay, this is the delta node. And after crossover points we can't calculate this one because this is bent. Okay, so this is not delta nodes, so we have to look that which is not bent. Okay, So we see that this T2 is not bending. This is go straight away because there is no problem with this T1G and this. Another edge we see here, this is going to straight, this one. Okay. So now what we will do that here T1G, here this is T2G. So this T1G and T1G get repulsions. This T1G and T1G get repulsions. Not T1G and T2G. T2G and T1G, they will not get repulsions. Okay. So this is straight and this is straight. So now we have to calculate that delta T from here to here. Okay, because this is get bent. Okay. So delta T will calculate from here to this A2. This will be the delta naught. So here see that 1.2 and this is that 0.8. So I will do that 1.2 delta naughts. So we can do that. We'll get 0.8 1.2 delta naughts minus we should get that one value. Okay, so 1.2 delta naughts, and how will get 1, and that you have to do the plus no delta naughts. So this is the delta naughts. Okay, so what you do that 1.2 delta naught plus uh, minus 0.8 delta naughts. So here we did that this is that 1.2 delta naughts minus 0.8 delta naughts. That is going to be that this will get subtracted. So that is 1.2 and this is 0, then that will be going to be 4. No, you should get 1 delta naught. So that delta naught will be always 1. Okay, so if that is correct, so here you see that 0.8 and 1.2 delta naughts. So if I do that 1.2 delta naughts, okay, this I will subtracting this minus of 0.8 delta naughts, then this is going to be 1.2 delta naughts plus 0.8 delta naughts. That is going to be that 0.2 delta naughts. So this is we should get that 0.1 delta naughts. This delta naughts, so this is minus 0.8 delta naughts and plus 1.2 delta naughts. Just a minute, this value has to be 1 delta naughts. Oh shit, we did that wrong. That is that Orgel diagrams is, so this will assign T2G. Okay, this value is, let's rectify this. This is T21G and this is T2G and T1G, and this will be always the T1GF, not T2G. Okay, so this T1G and T1G. Okay, this is the same, this is the T2G, so this value is T1G, not T2G. Okay, so that the get wrongs here. So this is T1G, this less value, this is the 0 ground state here, so this is the T1G, this is the T1G, and this is the T2G and T1G, and this is the A2G. So this and this will get repulsions. Okay, so this is very high and this is there, and so this is Orgel diagrams we will draw again. Sorry for the confusion, so I will do again. Okay, so here that DF3, and it will be like this, and it will be like this. So let's say that this is that 3T1G, and this is that this is this is minus 0.8 delta knots, and this is that T1G P plus T2G. This is for 0.2 delta knots, and another is A2G, A2G, and this is 1.2 delta knots. Okay, that I put here, and now that A2G, sorry, that excited state 3P, this will comes here and this will cross here. Okay, this is the crossing points. After that, this is that this is T1G, this value is T1G P, so this is T1G, and this is also T1G is there, and also this is the T1G is here. Okay, so whenever they come closer, then only there will be repulsions will happen. Okay, so this and these are coming closer. Here also T1G is there, this is also T1G is there, so now it will do the repulsions here after crossing points. Okay, and this also get repulsed because here also T1G is there, this is also T1G, this is get repulsions will occur here. Okay, but here this is the T1G, but this is very far away from it, so it will be not repulsions because this is going here down. After crossover point also this will be in the straight line, so here the repulsions will be happened. So here will be that line is not straight, that will be get bent. Okay, so now what you see that this is the cross points, this is the crossover points. Okay, so now this delta knots from here to here, that is for that weak field ligands, and whenever that strong field ligands, we will weak field ligands for delta knot calculations. Okay, so the delta knot calculations, if it is weak field, then we will calculate here and here, that we will calculate delta knots if strong field ligand is given. Okay, so after crossover points, okay, this is the crossover points, this is the line of crossover points. So here that all that weak field ligands we will calculate, weak field ligands the delta knots, here we will calculate that strong field ligands delta knots. Okay, this is the crossover points. Okay, so now what you see that always the delta knots, whenever you calculate that I call delta knots, that always we get the 1. Okay, so here that but where is that delta knots for if that weak field ligands is there, then if that weak field ligands is there, the delta knots will be, let's say 0.8 and this is 0.1, so from here to here. Okay, this is the delta knots. So if you calculate it, we see that that is 0.2 minus 0.8, that is going to be that 0 going to be that 1. Okay, This delta knots has to be always 1. Okay, for the if weak field ligand. Okay, so that transition is from where T1G 3 to this is the T1GP, that is T1G 3 to T1G 3 plus T2G 3. This is the transitions. Here we will calculate the delta knots. Okay, this is the transitions. And if it is that strong field ligands, if it is strong field ligands, we will look that after crossover of points. So here, so this is get bent, this is get bent. Okay, so we can't calculate by taking this and taking this. So this is in the straight, and also this is in the straight. We see here this is get bent, and oh, I see. So there will be look that this is get mixed it up. So this pure T1G and T1G only get repulsions will happen. Okay, this is the T1G and this is the T1G. Okay, so here the repulsions will happen, here that repulsions will not happen because this is the mixture. So here that this will not get bent. Okay, the same mistakes I am doing again. So this is not. So this will get bent. See, this will get bent because same will be the if the same is that will get bent. So this and this will get bent because here this is mixed it up T1G and T2G, so it will not get bent. So it will go straight away like this. This will get bent and this will get bent. The same things will get bent. Okay, be note that. Sorry for the confusion. So always that same things will get bent. Okay, this is the T1G and this is the T1G. So this will get bent because this is the mixed it up. It will not get bent. Okay. So what are the bends? This and this. So what are the straight? This and this. So here we will calculate that delta knot. So delta knot will be here. Okay. So that delta knot, if you calculate, then that is 1.2 delta knots minus 0.2 delta knots. That is going to be delta knot. Okay. So sorry for the confusion. So be note that only if this is mixed it up, that will not get bent. Only that pure one will get bent. Okay, this one and this one. Okay. So this is the delta knots for if ligand is strong field ligands. Okay, and it is that if ligand is weak field ligands. So here the transitions is from that is from here to here, that is this one is A to G 3 to this is sorry, this is that T1G T plus T2G 3 to A2G. This is the transitions. Okay, so we will do then more so that we will get clear. Okay, thus we have did for that D2 octahedral. So now let's go for D2 tetrahedral. D2 tetrahedral. So we will fill here, that will be here 3 orbitals, here 2 orbitals. Okay, so 2 electrons are there, 1 and 2. Okay, so now I am doing that electron 1 transition. So again, that electrons, how many transitions are possible? 2 transitions, and for hole we have that 3 is possible. So we will discuss according to electron, not according to the hole. Okay, so I will do the 1 transitions. If I do 1 transitions here, then this will go here. This another transitions if I do, then this. Okay, so now you see that here this is that so T2 also the but either a octahedral or tetrahedral, that is F3, and it is has that T2G, T1G and A2G. Okay, so here I will assign that A2G because this is not non-degenerate state is there. So I will assign here A2G, and here I will assign either T1G or T2G, and you see that here doubly degenerate both are degenerate state is there. So I have to assign 2 values. Already I assigned A2G, so this 2 has left. This 2 I will assign here. Okay, and this is always that excited state, it never be the ground state. So this will be the T1G P plus T2G. Okay, and this will be the T1G. Okay, T1G, that is F. Okay, this is the excited state. Okay, this is that this is for not excited state, not excited, not like that. This is for excited state, and this is for other. Okay, now we calculate the CFSC value. So this value will be here. You see that now here 0.6. Okay, this is 0.4 because 2 6 to 12 for 3, that is 12. Okay, so same should be get 12. So this 6, that is equal to minus 1.2 delta knots, and here that CFSC will be this is 0.6 minus 0.6, and this is plus 0.4, and that is going to be minus 0.2. Okay, and here that is going to be that 0.8 delta knots. So this is not delta knots, this is for delta T. Okay, this is we are talking about a tetrahedral. So if I anywhere if I do my mistake delta T, then please correct it. This is delta T because we are talking about a tetrahedral. Okay, so now we will draw that Orgel diagrams. Okay, Orgel diagrams. So this is F3 3A. Okay, so I will do here. So less energy each, which one have that the ground state. So now this A2G is the ground state. Okay, this is that A2G, and its value is minus 1.2 delta T, and this values, and this is minus 0.2. So this is the past excited. So I say that this never be the ground state. Okay, so this will be the so you see that this is also negative. So if you say that any value that is in the positive way, let's say this is the delta knots value, so that is positive. So here also this is also come like this. Okay, this is T1G plus T2G, and that is minus 0.2 delta T. Okay, because this is the negative values. This is the negative values. Okay, past is 0.2 delta knots, 1.2 delta knots, this is 0.2 delta knots, another is 0.8 delta knots. So whenever it is negative value, always draw below it. So let's say this is the positive, after that is the negative. Okay, another is 0.8 delta knots, that is let's say T1G, that is 0.8 delta T. Okay, sorry, confused. This is that delta T. So now we'll do that excited state. Excited is always T1G P. So here we see that this is the T1G is there. Now I'm going that accepted state here. Let's say 3p. This is for 3f. This is 3p. This will be get repulsions, because this is also, so no crossover points you will get here. Okay, because whenever the lines of the same symmetries approach each other, they never cross. Okay, there will no crossover point. So here that for strong field ligands, so we are used to calculate that strong field ligands after crossover point. So here nothing like that will come, because here that crossover point will not come. Okay, so here this, then we see that here we calculate that delta t values. So delta t values will be from this is 0.2. So this is T1G, and this is also get like that, repulsions will happen. Okay, so here this is also get repulsed, this will get. So these are the bend. So using this we can't calculate the delta t. The lines which is not bent, there only we will calculate the delta t. So I will have to use this one values. Okay, this is the delta t. Okay, so that is minus 0.2 delta t minus and minus 1.2 delta t. That is going to give that minus, this is minus 0.2 delta t, that is plus 1.2 delta t, that going to get 1 delta t. Okay, so this is the delta t for this, and in this case there will be no crossover points, so there will be no like weak field ligand, strong field ligand. So everywhere this is applicable, means that for weak field ligands and for strong field ligands the delta t will be the same. Okay, both for weak field ligands and strong field ligands delta t is same. Okay, if that these things is happen, like, so there will be no crossover point, there will be that line is bent. So here also there will be no crossover point will come, because the symmetries are very nearer to each other, so they will cross it with each others, and there will be no crossover points. This is that value, that is 3T1G. Okay, this is the for T2 tetrahedral. Now we will go for that another is D8 octahedral. So in type 2, what are there? T2, D8, T3, D7 is there. Okay, so we have completed D2. So we have completed D2 for both octahedral and tetrahedral. Okay, now we'll go for D8 octahedral and tetrahedral. Okay, so for both the cases we will look for octahedral, and I will draw here also D2 so D8 tetrahedral. Okay, so for D8 we see that we will fill the electrons. So then let's fill. And this is the electrons for D8 also I am filling. Both case I will calculate. Okay, so I am filling the electrons. See, for D8 octahedral, so this is always that high spins. So fill the electrons with the two. So so 1, 2, 3, 4, 5, 6, 7, 8. So here that if I do that electron transition, then 2 transitions are possible, and for that hole also 2 transitions also possible. So anyone I can take. So I am taking that electron transitions. Okay, because this is also 2 and hole also 2. Okay, so anyone I can take. I am taking the whole electron transitions. Okay, so now if I do the transitions here, then what things I will get? when I will do the transition. So okay, another transitions if I do, then this will get like this. Okay, so this is that D8 octahedral, and if I go for tetrahedral, oh set, this is for let's say G2 tetrahedral, and let's say here for octahedral. Okay, for octahedral, let's fill the electrons. So 1, 2, 3, 4, 5, 6, 7, 8. Here, if I do that one transitions, then this will go like this. This one transitions I did here. Okay, another transitions I will do. Then what I will get, this single, this. Okay, this is the one transitions I did. After that, another transitions I did. Okay, you can look it. Okay, this is the past case. 1, 2, 3, 4, 5, 6, 7, 8. After that, one transitions I did, then one electron goes from here. After the another transitions I did, the goes from here. Okay, so these are the octahedral and tetrahedral. Okay, this is the tetrahedral case, and this is the octahedral case. So now here also I did that. I will look that electron transitions, because two holes are there, and for sorry, here I will go according to that hole transitions. Okay, because see here that hole is 2 and electron transitions is 3, so I will go here, I will not go there. Okay, so hole transitions, you will see that here also 2 hole is created. Okay, from here 2 hole to here 2 hole created. Okay, here also 2 hole was there. Okay, this is the one hole, this is the one hole, here this is the one hole, and this is the one hole. Okay, so I will do that hole transitions here. Okay, here I will do that according to electron transitions. Okay, here hole or electron same is them, so you can do hole also, you can do the electron transitions also. Okay, so now we will calculate the CFSE value and assign that molecule notations. So you see that for D8 also, D2 and D8, that is F3, and it has that T2G, T1G, and for tetrahedral this is T2, T1, and another is A2. So note that wherever I do the tetrahedral, then we will not assign that G. Okay, please note that that is only A2. Okay, that G will not do, so please correct it. If that is tetrahedral, then G, this will be not come. Okay, if it is the tetrahedral case, it is tetrahedral, so that it will not come. Okay, please look that if that is tetrahedral, then this GU will not come. Okay, so now calculate the CFSE value for both the case. So here if I calculate that CFSE value, then what the CFS value, you see that this is cancel it up, this is 2, and this is for this 6, that is 0 1.2 for this, and this is 1, that is 0 0.4 minus 0 0.4, that is going to be get 0. This is minus, okay, because this is the negative side, so minus 1.2, and this is 0 0.2. This whole value is going to be get this is minus 1.2, because negative and 2 are there, because I know that I say that if fully filled, if all are half filled, that will cancel it up. So left which are that, for that we will calculate the CFSE. So 1.2 2 are there, 1.2, and this is 1 is there, and here we will multiply by 0 0.4, here we will multiply by 0 0.6, because 2. Okay, so that is minus 1.2 delta naught. I will calculate it. That is we will do the additions here. So this is 0.4 plus this is minus 1.2. So that value is going to get that value we are going to get that minus 0.8 delta t. Similarly here, and this is 2, so this is going to get 0.6 minus, and this is going to get how much value? So 2's are there, that is 0.8, that is going to get 0.2. okay, for this case we see that this is cancel it off, so here only there 1 2 3, so that is 1.2 delta t. okay, this is delta t. These are the CFSE value for this case. And for this case we will look here this case, and what is that values? 1 2 and this all are there, so this 3 has left here, and for this 3 that is 1.2 delta naught. okay, because this is for octahedral. okay, CFSE. And for this case, this is for this case, and for this case these are 2 are there, so that is case 0.8 minus, and this is that 1 is there, plus 0.6, so that going to get minus 0.2 delta knots. okay, for this case only 1 is there, that is minus 0.4, and this is 8, that is 12. okay, so plus 1.2, that is going to get 0.8 delta knots. okay, so these are that CFSE values. We see this and this. okay, so now we will calculate, we will look that declare that this is that one CFSE value, this is another CFSE value, and this is another CFSE value. This is for 1, this is for 1, and this is for 1, because according to CFSE value I am drawing that Orgel diagrams. okay, so now let's draw the Orgel diagrams. okay, so for this tetrahedral, this is for tetrahedral I am doing, and this is for octahedral. So for this tetrahedral, what I did here, what is that is I assign these values. So let's assign. So here see that both the cases degenerate state is there, so I'll do that T1G P plus T2G. okay, and this is here all are not degenerate state there, that is A to G. so this is tetrahedral, so this G will not come. This is A2. okay, and this now that here left is T1, so this is T1 F. okay, so these are that things. So now which is the lowest? So this, so T1F will be the lowest, after that 0.2, after that 1.2. okay, so what I'll do here, another is, okay, if that is positive value do this, if negative both are, then come to down like this. okay, another is, okay, so this is that T1G F, and this is that value is minus I think 0.8 delta T. this is not, and this is I think T1 plus T2, T1 plus T2, another is A2, this is A2. okay, and the accepted state will be drawn, and this value is, let's say 1.2 delta T, and this value is around 0.2 delta t, and this is 0.8 delta t. Okay, now that excited states will comes here. This is for pf and this is for 3p. Okay, so now this will comes here, so this value will be the t1, and here also t1 is there in the ground, so there is no much more repulsions will here, so it will come, it will cross these points. Okay, because this is here. Okay, cross will comes here. After that it will here, so some repulsions will be happen, because this is go here and this is goes here. Okay, after that the repulsions will start. Okay, so this line is get bent after that crossover points. After this point this will get bent. Okay, so since crossover point is happened, so from here to here we'll calculate delta t for weak field ligands, and here we will calculate for delta t for strong field ligands. Okay, so here the delta t will be delta t will be that this is already bent, this is, so for before cross point there will no bend is happened, so here we can easily calculate from here to here. Okay, so that we can calculate from here to here, this is the delta t, because before crossover point there is no bend has happened. Okay, so this delta t value is how much? This is 0.2 minus, this is minus 0.8, that is going to get that 1 delta t. Okay, but after crossover point this is get bent, so we will not use here, and this is the state, this is in state, and this is also in state, so we will use that for calculating delta t, these values. Okay, this to this is the delta t, and that value is 1.2 minus 0.2, that is going to be again 1. So this is the delta t for strong field ligands, this is the delta t for weak field ligands. Okay, so for weak field ligands the transition is what, where to where it happened, that is t1 f2 t1 plus t2, this is t1 p. Okay, so this is that for that, the here all are 3 this is that delta t for weak field ligands. So now if I talk about strong field ligands, then from here sorry, this is that what the values from t1 plus t2, this is 3 3 2, this is a2. Okay, so this is the delta t for strong field ligands. Okay, now we will move on to that delta t for strong field ligands. Now whenever if I move for octahedral case, how that this is the Orgel diagrams for that is what d8 tetrahedral, and this is d8 octahedral, the Orgel diagrams will be, let's say first we will put that CFSE values. So always do that excited state will be coming here, this is for 3f case and this is for 3p. Okay, because there is two states are there, one ground state and one other is excited state. Okay, so this is the ground state, in between that some ground state is there, and this is excited state, and this excited state we named that t1g from this, and we will do that excited state and ground state, if any they are crossing or not, we will look like this, and after that this will go. So excited state is always above and ground state is always low, and the Moltke notations will be drawn here. According to that we will calculate the CFS values. Okay, so for this case also I will do that two things, one is 3p, another is 3p. Okay, so this ground state, what are the things are there? So this is minus 0.2 delta t, 1 2 3, that is minus 1.2 into plus this is So CFS is right. So this is fully filled. So how many there? 1, 2, 3. So this is minus 1.2 delta t. Please note that this is 1.2 delta t and this is minus 0.2 delta t. Okay, and because this is that 1, 2, so 8, and this is 6. So this is minus 0.2 delta t and this is 0.8 delta t. Okay, this is 1, that is minus 0.4. This is 2, so 0.6. This is the value. Okay, this is the correct CFS value. So please calculate it. Now I will pull that Orgel diagrams here. So this is the ground state, and that is with that I will assign it. So see that here that all are no degenerate state is there. This is half filled, this is fully filled. So this I will assign to A2. Okay, because A2 represent that non-degenerate. So these are all non-degenerate. All are, this is fully filled and this is half filled. So degenerate state is not there. So I will assign A2, and this here you see that this is also degenerate is there. This is also degenerate is there. So for this I will assign T1G plus T2G. Okay, this T1G, this is that P excited state, and here what I will assign here, that here you see that here that degenerate state is there, here not is there. So this is only one, that is T1GF. Okay, now draw that Orgel diagrams for it. So this is the ground state, that is for A to G. So this is for a ground, this is for excited state. Ground state, what is that? T1GP is there. Okay, so this is, I will do that for A2. Okay, that value is minus 1.2 delta knots, and this is also negative is there. So negative means whenever negative, always down here. Okay, positive then go above. Okay, so this is down, so I will do that like this. So that is, and this value is T1G and T2G. So T1G plus T2G, and this is F, and this is going to give minus 0.2 delta knots. Okay, and this T1GF, that is going to above T1GF. So T1GF, that is going to get 0.8 delta knots. Okay, so now that here you see that this is also T1G has come, here also T1G is there. So now the repulsions will happen, so there will be no crossover of points. So this will goes like this, because this is the things has come. This is also T1G, this is also T1G. So this is also goes like this. Okay, so there will be no crossover points. So here no concept of weak filled and strong filled ligands. So delta T is same for all. Okay, so if I calculate delta T is here, then this is also get bent, this also get bent. So I always used to calculate from here only. So delta T is calculated where there is no bend. Okay, so the delta T is equal to how much? That is minus 0.2 delta knots minus 1.2 delta knots. That is going to be get delta knot. Okay, so this is the delta knots, both for weak filled ligands and strong filled ligands. Okay, so similarly where I did that Orgel diagrams for D8 tetrahedral and D8 octahedral. So we can look that where the transitions is happening for weak filled ligands and strong filled ligands. So here the transition is happening from that is A2 G2 T1G plus T2G, and this is 3, this is 3. This is the electron transitions. Okay, so similarly I have done that D8. Similarly we can go for D3. Okay, so D3 octahedral and D3 tetrahedral we can go. So let's do it, and that is octahedral. So I will do 2, 3. 2 3 3. Okay, so similar tetrahedral. Okay, so tetrahedral, so 3 electrons, so 1 2 3. Okay, and next I will do that one excitation. So here that electrons, 3 electrons are possible and hole 2 electrons, 3 hole 2. So I will do hole, not electron. Okay, this is one, let's say one transitions happened, another, let's say. Okay, so 2 holes from here, that is shifted to here, 2 holes. Okay, similarly for if this is tetrahedral, then 1 2 3, because always that is high spins only I will do. Okay, low spins can never be done, so I will do like this. Okay, so from here that calculate the CFSC values. So if I calculate that CFSC values for here, then this is that 0.3 will ascend, so that is 1.2 minus, okay, delta knots, because negative means this is the negative for negative, this is for positive. Okay, so here that how much, 0.8 minus, and this is 0.6, that is going to minus 0.2. okay, for this case how much, that is 1.2 minus 0.4, that is going to be 0.8. okay, so these are the CFSC values for this. This is the CFSC for this. Okay, so for this we will calculate the CFSC. So here now negative is here, and that is multiplied by minus 0.6. so this is 0.6, that is minus 1.2, after that plus 0.4, that is going to be I get minus 0.8, and here that CPSC value will be that here, that is multiplied by 4, that is 0.8, and minus 0.6, that is going to get 0.2, and here that is how much, that is 1.2, and this is minus 0.6, that is going to get 0.6. so these are the CFSC values for it. Okay, so now this assign that multiple notations. So here all are non-degenerate states is there. So this is that A to G I will assign. So you see that D3 and D7, that is F4 will come. Okay, so and F4 is again T1G, T2G, and A2. This is G for octahedral, and not G will be there for tetrahedral. Okay, so this will be assign that A to G, and this will be for a degenerate state is there. So I will assign this for that T1G F plus T2G, and this only here is only here degenerate state is there, so I will assign here T1G F. This is the excited state P. Okay, similarly here for tetrahedral, so here that all are that here only here the degenerate state is there, so this will be that T1 that is F, and this will be that both our cases are there, so this is that T1 P plus T2, and this is both the cases here. Anything wrong? So D3, so 1 2 3 1 2 3, so here electron is gone right here, so here only this is there, so here that no degenerate state is there, so this is the A2. okay, this is T1F, this is T1G plus T2, T1 plus T2, this is A2. So now we will draw the Orgel diagrams for both case. Okay, so now what is that there, here that grounds and the state is 1.2, that is for A2. okay, octahedral case. After that this is T1G and T2G, that is that, and that is also 0.2, and this is 0.8. okay, so here value will be like this, and also another also like this, another is like this. okay, this is minus 1.2 delta knots, and that is for A2G, and this is for T1G plus GF plus T2G, and this value we get that 0. Minus 0.2 delta knots, and this value we get that that is for T1G. I think this is for T1G, this is P. okay, T1GF, this we get that 0.8 delta knots. okay, it's fine. Yes, this the values. okay, so this is that ground state, and for the excited state I will draw from here excited state, because here for both ground state and excited are there. So here now what we'll do for excited state, this is always T1GP. okay, so this will goes, so here also T1G has came, so here this is also T1G, so this will no crossover points you will get, this will get ripples, and this also get repulsions will happen. okay, so here that no strong field and weak field will not look, we will calculate where that bend is not happen, here bend is happen, here bend is happen, so we will not use for delta T, so this will be the delta T. okay, so that delta T is how much, minus 0.2 minus 1.2 delta naught, that is going to be the delta naught. okay, and for that this is for D3 octahedral. Similarly, if I go for D3 tetrahedral, so you will look here that tetrahedral case, this is that for T1F is that lowest, after that this 0.2 and this is 0.6. okay, so here we see that T1GF, that is minus 0.8 delta T. after that 0.2. okay, for this T1G and T2. T1G plus T, G is not there for a tetrahedral case, we can't use T1 plus T2, and its value is 0.2 delta T, and other case is A2, and A2 is here how much, that is 0.6. 0.6, this is going to be 0.6. okay, delta T. So now we see this is the ground state, and for excited state I will draw here. So now this is excited is always T1, so T1, and this is also T1, so this is very low here, so here that crossover points will happen. okay, this is T1 excited state, this 3P. okay, so this will comes here and this will cross. So after crossover points there will be the repulsions. okay, so whenever they are not nearer, then after crossover point only there will be repulsions. Before crossover point there will be no repulsions will happen. okay, so after crossover point repulsions will happen. So this is the crossover points. So before crossover point, this is for the delta knots for weak field ligands, and this is after crossover point, this is the delta knots for strong field ligands. okay, so for this weak field ligands is given, then delta knot will be here, that no repulsion, there will be no any that bend will not there, so you can calculate from here to here, that is 0.2 to 0.8. so you can calculate delta T, then that is going to be that 0.2 minus 0.8, we will get the delta t. Okay, and for this, after crossover points, here will be bend is happened, so we can't calculate it here, so we will calculate where the bend is not happened. So here and here, if the bend is not happened, so this is the delta naught for strong field ligands. Okay, so delta t for strong field ligands will be that this to this, that is that what the values 0.6 and 0.6 plus 0.2. Something maybe get wrong, so because this will be net, that value should be always 1 delta. Okay, look here, this is 0.2, so this is the value and this is that negative, so I mean this minus 0.6 and this is 4, so 0.8. okay, so minus 0.6 plus 0.8, that value should be 0.2. okay, this is right, and for this case a2, so this is 4, so 0.6 here, no electron is there, so why? Okay, so this value will be that all other than 1.2 delta t. okay, so this value is not 0.6, that is 1.2, that is 1.2 delta t. okay, so this value will be 1.2 minus 0.2, so that is equal to 1.2 minus 0.2, that is going to be the delta t. So this is not 0.6, that is 1.2 minus 0.2, that is going to be the delta t. So this is the for strong field ligands. okay, similarly with D3 octahedral, and this is for D3 tetrahedral. okay, the Orgel diagrams. Similarly, we have left with D7 octahedral and D7 tetrahedral. okay, so in the same way we will calculate it. So let's do one. We have calculated lot. So let's say that because here the two transitions is happened, that's why I'm doing that this amount of diagrams here. Here also, here the tetrahedral, so this will come above. okay, so this is D7, so fill that D7. so let's fill that 1 2 3, always this is high speed, 4 5 6 7. okay, so one transitions I will do, then this will get double this one, and from here one I will go. okay, now again one transitions, so this. okay, similarly for tetrahedral, so 1 2 3 4 5 6 and 7. okay, so one transitions I will do, 1 2 3, one I will do excited states, again another one I will do, then this will like this, and this will be this. okay, so these are that things. Now calculate the CFSC values for the case. CFSC value will be that here all are fully filled, and this is that 1 2 2's are there, so this is negative, that minus 0.4, so that will be minus 0.8. okay, this is the delta nodes for this case, and for this case that is 1 is there, that is minus 0.4 plus this is 1, that is 0.6, that is going to be 0.2, and here that is these are that not there, here 2 are there, so these are that positive value 1.2. okay, 1.2 delta nodes. Okay, this is the CFSC. For this case we can calculate its CFSC values. So here that this is that there 2 are there, so that is going to be that 666, because here multiplied by minus 0.6, so this is 2 into 6, that is minus 1.2 delta t. And for this case only 0 minus 0.6, and this is 1 plus 0.4, that is going to get minus 0.2. and for this case these are negative is not there, only this 1 2, that is going to be 0.8 delta t. Okay, now assign these values. So d7 also you see that so d3 and d7 we see what that is going to be get that value on f4, and whenever f is there, here also the t1g, t2g and a2g is there. Okay, this is 4, this is 4, this is 4. Okay, so here also I will assign the same, that is here that all are here, that here also, here not degenerate, here degenerate state is there, and here that all are degenerate state is there. So this is for that a2g, and here that both are degenerate state is there. So I will assign here that t1g plus t2g, and here only this is accepted, this degenerate state is there, so I will assign here that t1g f, this is t1g t. Okay, now same things here I will assign. So here that these values all are that non-degenerate state, so here I will assign that a2, and here this also degenerate state is there, so I will assign here t1g p, or tg will not come, plus t2, and here only this is there, so this will be t1 f. Okay, so this p generates that excited state, this f generates that state, that ground state. So let's draw the Orgel diagrams. Orgel diagrams. Okay, for here that first is f for, another is p for, that is for p. Here also f for, another is for p. Okay, this is that ground states, and this is the excited state. This is the ground state, this is the ground state, this is the excited state. Okay, so in the ground state what are the here? So here we see that the whatever the ground state will do and excited state will be drawn from here. Okay, ground state, what are the that? This is the 0.8 minus. Okay, so that will comes down, that is t1gf. Okay, this will be the t1g f, then t1gf, then this will be the t1g and t2g, because t1g and t2g always in the then t1g and t2g. t1g, this is f plus t2g. Okay, and its value is minus 0.8, and its value is 0.2. Okay, now that this values, that is a2g, that value will be that a2g, this is 1.2 delta nodes. Okay, so now this excited state is t1g, this is always t1g p. So this t1g p will be, this is the t1g and this is t1g, so here crossover point will happen. Here crossover point will happen, so here the cross is happened. After that you see that after crossover point only the repulsion will happen. Okay, this and this, so this will got repulsions and this will got the repulsions here. Okay, so that delta t values before, this is the crossover points, So this is that for weak delta T for weak field ligands, and this is the delta T for strong field ligands. Okay, so here the delta T will be from here to here, because before crossover points there will be no any repulsion, so this is not bent, so you can easily calculate from here to here. That is 0.2 minus the 0.8, we will get the delta T value. Okay, and after crossover points, this has not bent, this and this, so this and this is the delta T values. Okay, similarly for if I go for that this case, that 1.2 that values, and that is maybe A2. Okay, here that A2 is the ground states, here A2 that is minus 1.2 delta T, and that values, yes, and A2G and T2G, A2 this values, this is for T1 F plus T2, this is for minus 0.2. Okay, and now that A2 and T2, and next is .8, that will going to get 0.T1 this is T1 F, this T1 F is what, 0.8 delta T. So this ground state source, note that this value is only for this is only for T2, we will draw here. Okay, this is for A2, this is for T2, and because T1 I am doing that that excited state, so now that excited state will be T1, so this will be, that will be that going to be, so T1 here also T1, so this will be that like this, so there will be that no crossover point will come, so the delta T will be, so the delta T will be any values of this, because here that this is bend is happened and this is also bend will happen, so only this has not bent, so this is the delta T. Okay, likewise we can calculate for D7 also. So I have did that here D7, and D3 I think I have done, yes, D3 also done, D7 also done. Oh, I see. So D3, D7, D2, D8. Okay, so we have done the all the Orgel diagrams. D7 also we have done. Okay, so we have done that all that Orgel diagrams. So likewise we can draw the Orgel diagrams. So these things if you draw it, then it will take lot of time. So likewise that one electron type 1, there one electron or one hole transitions was there. Similarly here also we can draw that one diagrams, from that we can understand that whole things like shortcut way. Okay, so this diagrams, so that is for that understanding. Actually you have to know this one. Okay, these diagrams, you have to remember only this diagram. Okay, so the combined diagrams we can say. So this is that ligand field strength, and this is that energy, let's say. So what we see that here, that T1, so because always we do that T1, then T2, then A2. Okay, so this T1 will be goes here like this, if you say T1, or I can say T1 and T2. Okay, this is the T1 and this is the T2. Okay, then this is T1, then this is T1, and this is T2, then sorry, this is T1, this is T1, then this is T1, this is T2, then this is T2. Okay, and now A2 will be somewhere like this. Okay, this is the A2, sorry, this is the A2. Okay, this is the A2. So the transitions, what you remember here, that for one electron transitions we are doing the D2, and for that we did remembering the D1 and D6 for one electron transition, or one hole. Okay, so now here we remember that D2 and D7, just one D2 and D7. So D2 and D7 for octahedral case, and opposite of it, that will be D8 and D3 for tetrahedral case. So for this type of transitions, for this, the transitions will happen from here to here. This will be always the ground state. This T1G, that is F, and this is T2, that is T1G, and this is A2G or A2 or T2, or this is T1G or T1. Okay, so for octahedral D2 and D7s, the transitions are always from here to here, and for here or here to here, and for octahedral and tetrahedral. And for here, in this case, for octahedral, just opposite of that, that will be the D8 and D3, and tetrahedral case, that will be the T2 and D7. Okay, so this is that for this type of the, and transitions will be always the ground state will be A2, and this will go from here to here. Okay, so here you see that we can look that, and one more thing, that excited states will comes from here. Sorry. This is the T1. Okay, and for that that ground states which comes from here to here. Okay, here that no any crossover points will happen. Okay, so because this will not comes from here, that is excited state, that is T1P will comes here. Here that crossover point will happen, T1P. So this we have to remember. I think this is the same. Okay, so yes, so here there will be no crossover of points. We see that there is no crossover point. For this case, the crossover point is there. So we see that D2, D7, D8, D3, only that crossover point, ligand and strong field concept is there. And for D8, D3, D2 and D7, there will be no crossover points. So this is that combined for all the cases. Okay, so if you remember this, I will draw again this one in a nice manner. Let's do it here. Then this is ligand field strength, and this is ligand field strength, and we see that here first we will go for D1, D2 and A2. Okay, so this D1 will be here, let's say D1, and let's say D2. Okay, and this is T1, this is T2. So if T1, then this is T1, this is T2, this is T2, and A2 will be here. This is A2, this is also A2. Okay, and that this is for ground state and the excited state. Here that from here that no crossover point will be here, that will be cross here. Okay, so here that crossover point will come. This is for strong field weak field ligand, this is for strong field ligand. So here crossover point will come, here crossover point will not there, and this type of transitions will happen where, or so you can remember that for single electron transitions where we are looking for D1 and D6, we are looking for single electron transitions. Okay, that for type 1, this is for type 1 you are looking. So for type 2, for this type of electrons where you look here, that is just add it D2 and D7. Okay, so I erase it. This is for octahedral. Okay, and for tetrahedral, just opposite of D2, that will be D8, means adding so that will get 8 10. Okay, and this D7, then I will get D3. So this type of transitions, this type of the transitions will be from here. Okay, so here that crossover point, then the repulsions will happen. Okay, after that repulsion point will happen, so that structure will be drawn like this. Okay, and for this there will be no repulsions, there will be the repulsions will happen. So this is the T1G, because this is also T1G excited state, this is also T1G excited state. Okay, so this is T1G and T1G is here. So after that here the repulsions will happen. Okay, so after this repulsions will happen, so the transitions are, so from here to this is T2 and T1, so transitions are always from here to here. Okay, and here that repulsions happened, this is also repulsions will happen, so the transitions are from here to here. Okay, so this is the always for this type of octahedral. This is that D2 and D7. So octahedral case, for this case, so tetrahedral will be, octahedral will be D8 and D3, and tetrahedral will be that D2 and D7. If this type of this there, then this type of will be followed. Okay, and this is there, if this is there, this will be the follow. Okay, this transitions, this will be the delta T. For this case, this is the delta T. Okay, so whenever that transitions is there, you see that wherever we have drawn all this Orgel diagrams, so you can notice that wherever D8 D7 is there, there will be the no crossover point. Octahedral D8 D3 and tetrahedral D2 and D7s. Look, D2 and D7s, D2 and D7s. For if I look for, so this one erase it, something wrong has happened here. Not consider this. Consider this Orgel diagrams. Okay, so for all these things, then we will okay, so for this, let's see that D8 and D3 octahedral case, there will be no crossover points. Okay, so D8 and D3 octahedral, look here, this is D3 octahedral, no crossover points. Similarly D8 octahedral and D2 octahedral, right? So we can match with this. So whenever that D8 and D3 octahedral, there will be no crossover points. So here you see that this is D2 octahedral, no crossover points. Similarly D8 octahedral, no crossover points. Okay, so similarly way, so this is the combined for all. So from this we can conclude that whenever the d8, d3 and d2, d7, so unlike drawing all these Orgel diagrams, CF is calculated, you can draw these diagrams and you can understand that where it is. Okay, and we note that I drawn here that this is T1 and T2. This is only for T1 because T1P is gone here, so this is only T2. Okay, sorry, yes, this is only for T2 because T1 I have drawn here, so T2 is not there. So this one, wherever I drawn the T1, T2G, so this is only for T2. Please correct it. Whenever I drawn the T1G and T2G, because T1G this is the accepted state, so here only for T2G. Because T1G I already drawn here. Okay, okay, so likewise you can do. Okay, so please correct it. Wherever I drawn the T1G and T2G, only T1 T2G is there, T1G I am drawing here, but both time T1 T2 cannot be drawn. Okay, so we have discussed that for all this case, if I get the summary of Orgel diagrams, summary of Orgel diagrams. So what we are doing here, we are doing for transition metal complexes. So what we say that Orgel diagrams, this is the correlation diagram where we are looking at relative energies for terms in the transition metal complexes. Okay, so transition metal complexes means they will use the D1, D2, D3, D4, D5, D6, D7, D8, D9, okay, and D10. This type of that they use their transition states. So this I will divide into three types. So one is I will do the type 1, another is type 2, another is type 3. Okay, so in type 1 that falls, that is D1, D9, D1, D9, and that is I think D1 that is D4 and D6. Okay, and for type 2, and this one D1, D9, D4, D6, and for type 2 remaining, that is D2, D8, D3 and D7. Okay, and this is 1 2 3 4 5 6 7 8. So 1 2 3 4 5 6 7 8 9 10 11. So left are D5 and D10. Okay, all I have used. D1 is there, D2, okay, D9 and D8, okay, D4, D6, for D6, and then D3, D7, D3, D7, 1 2 3 4 5 6 7 8 9 10. Okay, 1 2 3 4 5 6 7 8 9 10. Okay, so all I have used. So type 1 is this and type 2 is this, and type 2 3 is this. I says that for this no Orgel diagrams, because I say that Orgel diagrams where spin should be allowed, but here that spin is not allowed. So here spin is not allowed. For Orgel diagram condition is spin should be allowed. So here spin is not allowed. Here spin is not allowed. So for this no Orgel diagram drawn, so these are the colorless. Okay, so for type 1 and type 2 I have such, and for this is that one electrons or one hole transitions will happen, and for this two hole or two electron transitions will happen. Okay, and for this type of diagrams what I say is that we have to remember these Orgel diagrams. For this Okay, so here that what I said, we can remember always that octahedral case, this is EG and this is T2G. So first I will do that. Okay, that is T2 and this is E. So this is T2 and this is E. Okay, EG or T2G or T2 or E. Okay, and this is for and this is for that case where I said that what you have to remember, that is D1 and D6. Okay, this is for octahedral, and tetrahedral will be just opposite of this. Opposite means D1 adds so that I will get 10, that is D9, another is D4. So for this type of d orbitals, this type of that, the transitions will be always for T2G to EG. This type of transitions you will get. Okay, so this is T2G, this is again T2G, and this is again EG or E T. Okay, so this is the octahedral. So this octahedral, so tetrahedral will come here, D9 and D4, and this just get reverse of. Okay, tetrahedral case, this will be D1 and D6. So this type of transitions are there. This will follow this, and if this is there, this follows this, that is from here to here. Okay, this is for one electron transitions or one hole is there, type 1. For type 2, what you see here, for these things, what you see here, that T1 and T2 first. Okay, that is like this, T1, T2, and this is A2. For that diagrams, that is here we will draw that T1 G or T1, this is T1 G or T1, and A2, then T1, then T2. Okay, this is T2 G or T2, this is T2 G or T2. After that I will go for A2, this is A2 G or A2, and this is A2 G or A2. So after that, here that now crossover, here not to come for here, that this from here it will start, and here the crossover point will happen. After that it will do the repulsions. So this is that T1 or P. Okay, then that is G for that octahedral, not G will there for tetrahedral. So this is a T1G or T1 etc state. Okay, so now that here whenever the same things will come, the repulsions will happen. This is here, so here the repulsions will happen like this, but here that this and this are very nearer, so this will, the repulsions will happen. So that wherever that bend, there will be no that delta T is not able to calculate. So the that are not bent, so here to here after crossover points, and before crossover points we can calculate from here to here. This is delta T and this is delta T, and this is that crossover points. This is for that is weak field ligands, and this is for strong field ligands. Here no such things are there. Okay, this is both SFL and weak field ligands. Okay, so this is that for type 2 transitions. Here the transitions will be that here the repulsions happen, so this is the delta T. Okay, so but for this case, this is the delta T. For strong field ligand, weak field ligand, this is the delta T. Okay, so transition is like this. So for Orgel diagrams, if you look this page also, it is fine that how that and here that no Orgel diagrams for type 3, and these are the colorless compounds in Orgel diagram. Okay, so this is the summaries of that Orgel diagrams, type 1, type 2, and type 3. Okay, and we see that this Orgel diagrams is drawn for only for high spin complexes and spin allowed transitions, and if the same symmetries are come, they will always repulse. Okay, so that conditions we have to look, and we will look this last page, then it will clear. Okay, so today up to this, thank you.